So in this short video, we're going to be looking at the following skills which come in the biology papers, chemistry papers, or the physics papers at GCSE. We're going to look at how we can describe relationships from a graph. We'll look at how we can describe them from a bar chart, and also how we can describe them using a table of results. We're going to check we know how to measure the gradients of straight line graphs, and then go on to higher level questions and skills which look at how we can measure tangents of the curve, which calculate rates, how we can prove directly proportional relationships using data where the independent variable doesn't increase in a regular fashion, and same with proving inversely proportional relationships where again our independent variable doesn't increase by the same amount each time. So firstly, describing relationships. It's pretty easy to do this as long as you make sure that you remember to look at your graph and use the words that are on the x and the y-axis and just say, as the mass increases, then the volume increases. Now that's worth 1 mark, and in most describing questions it's worth 2. So you have to talk about the shape, and of course it's a straight line going to the origin, which means it's directly proportional. As you double one thing, the other one doubles. So what about the next one, if it's a curve? Well, first of all, you say the same thing again. You say, as you increase the time, then the volume of gas increases. Again, that's only worth 1 mark. If I increase the time by 10 seconds each time, then you will see that the volume is going up by less and less each time. So that's the next thing we can say. As the time increases, the volume of gas increases by less and less each time. And then finally, of course, you will see that actually the volume stops increasing at 28 seconds. So that is how we get our 3 marks for that one. So again, the next one is about current and potential difference, and it says describe and explain the relationship shown in the graph for a filament bulb. So I always try and make sure I highlight that. There's 2 command words, so I've got to make sure I do both. Firstly, the basic pattern is, again, as I increase the potential difference, the current increases. That will give me my 1 mark. Then, of course, it's not a straight line, it's a curve. So remember, if I increase the voltage by the same amount each time, you will see the current is going up by less and less each time. So we can say that. However, as voltage increases, the increase in current gets less. And that will give us another mark. Finally, I've got to explain the relationship. This is because the resistance of the bulb increases because the temperature of the bulb increases. So that was my describing, and this is my explaining. So I've answered both the command word questions. Now let's have a look at describing relationships using data instead. It says the bar chart below shows information about the number of deaths per year in England. And it's from either this disease here, MRSA, or C. difficile. Now, look carefully at the graph. You can see that this is a C. difficile, and this is the MRSA. And it says describe the trend in deaths caused by C. difficile. Trend means pattern. So you can clearly see that as I increase the number of years, then the number of deaths from difficile decreases. That's the first thing I can say. So the deaths decrease each year. But of course, again, it's worth 2 marks, and I've only made 1 statement. So let's see how they do decrease. You can see that it decreases by that much on the first one, then by that much again, and that much again. So you can see the decrease in deaths is getting less each year. So the decrease is less each year would give me my 2nd mark. So always, if it's 2 marks, make sure you're making 2 statements. So we're now going to look at patterns in data. The first thing is to remember is on a table of results, your independent variable will always be first. This is the one that you are changing. And your dependent variable will be here. This is the one you're measuring. This depends on this. So extension of the spring depends on the force you apply. And always start basically. So if I've got to describe the relationship between the applied force and extension, this is worth 3 marks. How can we get 3 marks out of this? Well, first of all, as the force increases, the extension increases, will give me my first mark. Secondly, just like the straight line graph, I'm looking for a relationship. And you can see that as I increase the force by 0.5 each time, can you see the extension is going up by the same amount each time? That's 0.025. Going from there to there is also 0.025. And going from here to here is also 0.025. So they're going up by the same amount each time. So we could say, as we increase the force by 0.5 newtons each time, the extension goes up by the same amount each time. This means they're directly proportional. The other thing you could say is that as you double the force, you can see from 0.5 to 1, this doubles as well. So you can say as the force increases, the extension increases. Extension is directly proportional to the force. If you double the force, the extension doubles. So what about this one? Well, you can see as well, this is your independent variable and this is your dependent variable. And you're increasing the voltage by 2 volts each time. So you're increasing the independent variable by the same amount. So what happens to the dependent variable? Well, that increases by 8, the power increases by 8 again, and the power increases by 8 again. Now you can see that also increases by 8, but this one only increases by 6, and this one increases by 4. So if your independent variable increases by the same amount as your dependent variable each time, then you can see it's going to be a straight line, it's directly proportional. But towards the end, it's no longer directly proportional because it's not increasing by the same amount. So we can say up to a potential difference of 8 volts, power is directly proportional potential difference as it increases by 8 watts every 2 volts. After this, the relationship is not proportional or non-proportional or non-linear as the power goes up by 6 watts, then 4 watts. So always remember to look at how much your dependent variable is going up by. So let's now have a look at another pattern. This is inversely proportional. So you've got the thickness of lead in centimetres and you've got the count rate from the Geiger counter in counts per second. Notice as well my independent variable is going up by 0.5 each time. And it said the teacher concluded that the count rate was not inversely proportional to the thickness of lead. Explain why the teacher was correct. And it says use the data. So if I don't use the data from table 1, I'm going to get no marks. Now you've got to make sure you understand what inversely proportional means. So inversely proportional looks like this, which means if you double the thickness, the count rate will halve. So we've got to prove this, and it's best to prove it twice. So what I'm going to do is I'm going to double the thickness. I'm going to start from 10 to 20, from 0.1, sorry, I'm going to start from 0.5 to 1. So if I do from 0.5 to 1, we should find the count rate drops from 110 to 60. So 6 divided by 110 is 0.55, which is nearly drops to a half, nearly. But let's have a look to see if it does the same again. So I'm going to go from 1 to 2, and this time it drops from 60 to 18. Now it should halve, and of course 18 divided by 60 is 0.3, not 0.5. So it clearly does not halve. which means that it's not inversely proportional because the count rate should drop by half when you double the thickness, and that's clearly not the case. Finally, the last thing I want to do with foundation is to check that you can calculate gradient and units. So it says the graph below shows the volume of gas produced when different group 2 carbonate W is heated. Now, we saw this relationship at the start and we decided it was directly proportional. But this time it says calculate the gradient of the graph above, give the unit. Now, whenever you're asked to give a unit or significant figures, I would always do this. Where you've got to put your answer, I would write, so if your answer is meant to be written there, I'd write underneath it unit. So when you get to the answer, you remember to quote the unit, else you will lose a vital mark. So remember, when you're looking at graphs, to check that you know what the scale is first. So we've got 100 is in 10 squares, so 100 divided by 10 is 10, so each little square is worth 10. Now, of course, gradient is how much the y-axis changes for how much the x-axis changes. And if it's a straight line going to the origin, you can just draw 2 lines. And notice I'm going to choose a point where it crosses 2 bold lines. So have a look for that first, because if you get that there, it's easier to do. So you can see I've drawn 2 lines like that. And now my change in y, that's the y, my change in volume is 250 and my change in mass is 1.5. Notice I could have done it for this line or any of those lines like this, but this one is along bold lines, which makes reading the answers easy. So the gradient is y over x, that's 250 divided by 1.5, so the answer is 167, and that will give me 2 marks. But I haven't finished, because remember I'd written unit here to remind me, and the unit is just centimetres cubed. Do you remember divided means per, so per gram. So the final answer is centimetres cubed per gram. So if you're a foundation student, you can stop watching the video now. For higher students, these are some of the higher level skills which come in towards the end of your exam papers in biology, physics or chemistry paper, and these are the type of skills which students often lose a lot of markings but are easy to pick up. So this one is how the volume of gas changes against time, and it says use the graph to calculate the rate of reaction at 15 seconds, so that is here. Now remember, rate is how much something changes against time. So it's actually the gradient of the graph. Now what we want to do is to draw a tangent at this point. I'm just going to show you, I'm going to sketch it here first of all. So when you want to draw a tangent at a point like this, you need to try and draw something like that. Now there's a key skill here. It is much easier actually to draw a right angle that way first and then draw the line there. So first of all, I'm going to draw a right angle line to this point here, to this graph here at 15. Now that makes it much easier now for me to draw the tangent, which is at right angles to this line. And all I then have to do is measure the gradient. So the gradient is the change in y over the change in x. I'm going to draw a triangle here, make it a big triangle so that there's less error in your results. And you can see here I've measured that as 54 centimetres and this as 30 seconds. So I've got 54 divided by 30 is 1.8 centimetres per second. So that's the rate of increase of volume. And that gives you an excellent 3 marks. Now, this was the mark scheme which said anything between 1.4 and 2.2 gains 3 marks. So they allow a bit of error in your judgment of drawing the tangent. So let's try this one. So with this graph here, we've got how temperature changes against time. and we're asked to use the graph to calculate the rate at which temperature is changing at 4 minutes for insolation in degrees per second. And notice straight away I've been given it in minutes, so we'll have to convert. So of course I need to work out the gradient at 4. So again, I draw a right angle at that point there, then I draw my tangent to the curve. Now I'll draw a triangle in a minute, but I want to make sure I know the scale to read it accurately. So I've got 5 squares in 10, so each square's worth 2 on the y-axis. On the x-axis, I've got 5 squares in 2. So 2 divided by 5 is 0.4. So the scale here is 0.4. Drawing my triangle, I work out that that's 11.5 minutes, and this is 44 degrees. So of course the gradient is y over x, which is 44 divided by, and of course I've converted 11.5 minutes into seconds by timesing by 60, and that gives me the answer there. So that is the rate at which the temperature changes against time at 4 minutes. So in this example here, and I've jigged this question up, this actually says years, but you won't have to do it in years, you'll do it in seconds. Okay, but it gives you an example of the skill you need. So it says, the graph below shows how the number of Americasium-241 nuclei in a sample changes with time. So we've got the number of nuclei, and we've got how they decay against time, and this scale must be in seconds if you're going to work out activity in becquerels. So that's why I've changed it. It is just an example. So it says, use the graph to calculate the activity of a Americasium sample at a time of 600 seconds. So, of course, activity is the decays per second, which, of course, is going to be the gradient. So again, at 600 seconds, I've drawn a right angle. I've then drawn the tangent to the curve at 600 seconds. I've then checked I understand the scale. 200 in 10, that means 200 divided by 10 is 20 in every square. This scale here, we've got 1,000 in 5. So 1,000 divided by 5, each square is worth 200. So drawing a large triangle here, I make that, this point here is 1,180. And on this scale, with 200 a square, that's 7,200, 400, 600, 800. So I make that 7,800. So the gradient is y over x, which is 7,800, divided by 1,180, and that gives me 6.61. That's how you work out the activity of a radioactive sample given the number of atoms and the time. Finally, the last 2 key skills that you need to be able to do, and they've asked these before in GCSE questions, and the majority of students cannot answer them. Now, this skill is needed when the independent variable does not increase by the same amount each time, because you cannot prove it's directly proportional because you can't do any doubling. So let me just show you this first to explain how to do it. If a relationship is directly proportional, then we know it's a straight line going through the origin. And with maths, you know that the gradient is m. So any point on here will obey a relationship. And the relationship is y equals mx. So if we divide y by x, we get y over x equals m. And of course, m is the gradient of the graph. It is a constant, the same value for this set of data. So all we have to do is divide y by x. You could do it the other way around, it doesn't matter. You'd still get a constant value. So dividing resistance by length for 3 different values to really check if you get the same value each time, they are directly proportional. So the question is, the resistance to the wire is measured at different lengths. A student predicts the resistance is directly proportional to the length of the wire. Use the data collected to justify if the data supports the student's prediction. So if we have a look, 19 divided by 24 is 0.82. Taking another data point, I've chosen the middle one, 36.9 divided by 45 still gives us 0.82. And finally, 73.8 divided by 90 also gives us 0.82. So I can conclude y divided by x is a constant value, so they are directly proportional. The student is correct. So that's how you prove things are directly proportional given sets of data. So what happens if you have an inversely proportional relationship to prove when the independent variable doesn't change by regular intervals? Well, let me go through this with you. The question says the volume of gas is increased and the pressure is measured. A student predicts that the pressure of the gas is inversely proportional to the volume. Use the data collected to justify if the data supports the student's prediction. So of course you can see the independent variable is not increasing by the same amount. So you would have the volume on your x-axis as the independent variable, and if you put the pressure on the y-axis independent variable, then the dependent variable, then of course as you increase the volume, the pressure goes down. You're going to get something like this, which is not a straight line. However, we've been told that it's inversely proportional. So instead of plotting that, we could plot pressure against 1 over volume. And if we plot pressure against 1 over volume, we know that pressure is proportional to 1 over volume. So that will be a straight line going through the origin, where the gradient, again, is a constant. So any point on this line will obey the following relationship. Pressure is equal to the gradient times by the x-axis. That's like y equals mx. Now, of course, again, m is constant. So, of course, we've got 1 over v here. So in order to get this to the other side, I've got to multiply. So I've got pressure times volume is a constant, which is the gradient. So with inversely proportional, instead of dividing one by the other, you multiply them and you should get the same value. So let's just check with a few of them. 20 times 15 is 3,000. 280 times 170, we get very, very close to the same value. Finally, 42 times 72, again, very close to the same value. So we can say volume times pressure is equal to a constant. So this proves that they are inversely proportional. And that is how you prove those relationships. And that is it. Thank you.